How old are you? No, wait. Before you answer, let me ask you a different question. How do you know how old you are? You say, I was born in such and such year, and now it's this year, so I subtract. Fine. But what did you really count? What thing in the universe actually ticked off those years? See, here's what's funny. You think you know what time is. You think you know what your age is. But I'm going to show you that your age, the number of candles on your birthday cake, that number is secretly counting something very specific. And when you understand what it's counting, you'll realize something beautiful and a little bit strange about the universe. By the end of this lecture, you will understand what every clock in history has actually been doing, from the shadows on a sundial to the atoms vibrating in the most accurate clocks ever built. And you will see that your age doesn't measure what you think it measures. It measures something far more interesting. Let's begin with a simple observation. You have a heartbeat. Put your fingers on your wrist right now. Feel that? That little thump, thump, thump. Now, suppose you were the first person ever to exist, and you had no clocks, no sundials, nothing. Could you use your heartbeat to measure time? Well, sort of. You could say, I'll meet you at the river after 1,000 heartbeats, and your friend could count their own heartbeats and show up roughly at the same moment. It works, kind of. But here's the trouble. Your heart doesn't beat at a constant rate. Run up a hill, and it speeds up. Take a nap, and it slows down. Get frightened by a snake, and it races. Your heartbeat is a lousy clock because it doesn't repeat at a constant rate. And that's the first thing you must understand about timekeeping. A clock is anything that repeats. But a good clock is something that repeats at a constant rate, over and over, reliably, predictably. Now, what could possibly repeat at a constant rate? The ancient people looked around, and they found something magnificent. The sun. It rises, crosses the sky, sets, and rises again, day after day. And it seemed pretty reliable. So they said, all right, one complete cycle of the sun across the sky, that's one day. And if you wanted finer divisions, you could watch the shadow of a stick. As the sun moves across the sky, the shadow moves across the ground. The shadow slides from one side, gets very short at noon, then stretches out on the other side. A sundial, the first clock that didn't need a heartbeat. The ancient Egyptians used sundials more than 3,000 years ago. They divided the daylight into 12 parts, which is where we get our 12 hours. At night, they looked at the stars. They noticed that certain stars rose at certain times, and they used these stars to track the night hours. But sundials have obvious problems. They don't work on cloudy days, they don't work at night. And the length of a sundial hour varies with the seasons, because summer days are longer than winter days. So people invented water clocks. A clepsydra, the Greeks called it, meaning water thief. You take a container full of water, poke a hole in the bottom, and let the water drip out. The level of water drops at a roughly constant rate, and you can mark time by the water level. Water clocks were used in ancient Egypt, Babylon, Greece, Rome, China, and many other civilizations. They were more reliable than sundials in some ways. They worked at night. They worked on cloudy days. But they had their own problems. The rate of dripping depends on the water pressure, which depends on how full the container is. As the water level drops, the pressure drops, and the dripping slows down. Clever engineers built feedback systems to keep the water level constant, but these were complex and expensive. Neither sundials nor water clocks were very accurate. Errors of 15 minutes per day were common. For most purposes, this was good enough. If you needed to show up at the marketplace around noon, a sundial could tell you roughly when that was. But for some applications, better accuracy was essential. But wait, is the sun really constant? Well, mostly. But careful observers noticed that the sun doesn't move at exactly the same rate every day. In winter, the days are shorter. In summer, they're longer. And if you pay very close attention, the sun seems to speed up and slow down a little throughout the year. It's not perfectly regular. So the sun is better than a heartbeat, but it's still not perfect. Now, Here's where it gets interesting. People kept looking for something more regular, something that would tick off equal intervals more precisely. And around the year 1582, a young man named Galileo was sitting in the cathedral in Pisa. He was supposed to be paying attention to the service, but instead he was watching a chandelier. The chandelier was swinging back and forth. Maybe a breeze had set it moving. And Galileo noticed something curious. He timed the swings against his own pulse. Not a great timekeeper, but good enough for rough measurements. And he found that whether the chandelier was swinging in a big arc or a small arc, it took about the same amount of time to complete one swing. Now, that's remarkable. You might think, well, if it swings farther, it has more distance to cover, so it should take longer. But no, when it swings farther, it also goes faster. And these two effects cancel out almost perfectly. Galileo had discovered what we call isochronism. Iso means same, chronos means time. The pendulum takes the same time for each swing, regardless of how big the swing is, at least for small swings. This was a revelation, because now you could build a clock that wasn't at the mercy of clouds covering the sun or your heart racing from excitement. You could take a weight, hang it on a string, let it swing, and count the swings. And you know what's beautiful about this story? Galileo was supposed to be praying. He was in church, and instead of listening to the sermon, he was doing physics in his head, timing a chandelier against his pulse. That's the scientific mind at work. Everything is interesting, even the things that are supposed to be distractions. Now, let me be careful here. The story about the cathedral might be a bit embellished. Galileo's student, Vincenzo Viviani, told this story many years later. Whether it happened exactly that way, we can't be sure. But what is certain is that Galileo did study pendulums extensively, starting around 1602. He understood their remarkable properties. Here's something else Galileo discovered about pendulums. The time for one swing doesn't depend on what the pendulum bob is made of. It doesn't depend on how heavy it is. A heavy lead ball on a string and a light wooden ball on the same length string will swing at the same rate. That's weird, if you think about it. A heavier object has more mass, but it also has more weight, more gravitational pull, and these two effects exactly cancel out. The increased inertia, the resistance to acceleration, is exactly balanced by the increased gravitational force. This is the same principle that makes all objects fall at the same rate in a vacuum. Drop a feather and a hammer on the moon, where there's no air resistance, and they hit the ground at the same time. The Apollo 15 astronauts actually did this experiment. It's a direct consequence of the equivalence of gravitational and inertial mass, which is one of the deepest principles in physics. So the pendulum is not just a timekeeper. It's a window into the fundamental structure of reality. The fact that it keeps constant time is connected to deep truths about mass and gravity. But Galileo never built a working pendulum clock. He sketched out designs. He told his son Vincenzo about the idea. But he died in 1642 before finishing it. It was a Dutch scientist, Christian Huygens, who actually built the first practical pendulum clock in 1656, and this clock was revolutionary. Before the pendulum, the best clocks were off by about 15 minutes a day. Huygens' pendulum clock was off by only about 15 seconds a day. That's 60 times more accurate overnight. Suddenly, you could tell time with precision that nobody had ever experienced. You could schedule meetings, you could coordinate work, you could run railroads eventually. The pendulum clock changed civilization. But I want you to appreciate how dramatic this change was. Before Huygens, people didn't really think in terms of minutes. They thought in terms of hours, maybe quarter hours. Appointments were imprecise. I'll meet you in the afternoon was good enough. After the pendulum clock, people started caring about minutes, then about seconds. The pace of life accelerated. Factories could coordinate shift changes precisely. Ships could determine their longitude at sea, which depends on knowing the exact time back at the home port. Navigation became far more accurate. And here's a lovely detail. Huygens' first pendulum clocks didn't have a second hand, but within a few years, as clockmakers refined their designs, They started adding second hands because the clocks were accurate enough to warrant it. The clock itself changed our concept of what precision was possible. John Harrison, an English carpenter who taught himself clockmaking, spent decades building marine chronometers that could keep accurate time at sea where the rolling of the ship made pendulums useless. His H4 chronometer, completed around 1759, was a marvel of engineering. It used a balance wheel and spring instead of a pendulum, and it kept time to within a few seconds a day, even on a pitching ship. Harrison's work helped solve the longitude problem, one of the greatest technical challenges of the 18th century. It won him a substantial prize from the British government, though not without controversy and delay. The point is, accurate timekeeping was so valuable that nations offered fortunes to anyone who could achieve it. But why does a pendulum keep such good time? Let me tell you the secret. It's all about energy and restoration. Imagine you pull the pendulum to one side and let it go. Gravity pulls it down. It swings through the bottom, picking up speed. Then it rises on the other side, slowing down as gravity pulls back against it. It stops at the other side, then swings back. And the key point is this: the force pulling it back is proportional to how far it's been displaced. When you have a force that pulls something back toward the center, and that force is proportional to the displacement, you get what physicists call simple harmonic motion. And simple harmonic motion has a wonderful property. The time for one complete cycle, one complete back and forth, depends only on the properties of the system, not on how vigorously you set it moving. For a pendulum, the time for one swing depends on the length of the string and the strength of gravity. Make the string longer, the pendulum swings slower. Make gravity stronger, it swings faster. But how far you pull it back doesn't matter, at least for small swings. This is why pendulums make such excellent timekeepers. They have a natural frequency built right into their structure, and that frequency is very stable. But pendulums have problems. You know what the biggest problem is? You have to keep the pendulum swinging. Left alone, air resistance and friction at the pivot will slowly bring it to a stop. So every pendulum clock needs some mechanism, an escapement, that gives the pendulum a little push each swing to keep it going. And that push has to be very gentle, very consistent, or else it will mess up the timing. The design of escapements became an art form. Clockmakers spent centuries refining these mechanisms. The verge escapement, the anchor escapement, the deadbeat escapement. Each one interfered less and less with the natural swing of the pendulum. But there's another problem with pendulums. They're sensitive to gravity, and gravity varies from place to place on Earth. At the equator, you're a bit farther from Earth's center, and you're moving fastest due to Earth's rotation, so effective gravity is slightly less. At the poles, gravity is slightly stronger. A pendulum clock that keeps perfect time in London will run slightly fast in Greenland and slightly slow at the equator. Also, pendulums are sensitive to temperature. When it gets hot, the metal rod expands, the pendulum gets longer, and it swings slower. When it gets cold, the rod contracts, and it swings faster. Clever clockmakers figured out ways to compensate for this, using different metals that expand at different rates. George Graham invented the mercury pendulum in 1721, where a container of mercury at the bottom of the pendulum would expand upward as the rod expanded downward, keeping the effective length nearly constant. But despite all these refinements, there's a fundamental limit to how good a pendulum can be. The period of a pendulum depends on the local gravitational field, and that field is affected by the tides, the density of the rock beneath you, even the position of the moon. A pendulum is always dancing with its environment. Now let me tell you about something much better. Imagine a tiny tuning fork. You tap it and it vibrates. It makes a tone, a very pure tone. And that tone has a frequency, a number of vibrations per second. A tuning fork vibrates at a nearly constant frequency because, just like the pendulum, it has a restoring force proportional to its displacement. The tines of the fork bend, and the elasticity of the metal pulls them back. Simple harmonic motion again. But a tuning fork is much smaller than a pendulum, and smaller oscillators can vibrate much faster, Instead of one swing per second, a tuning fork might vibrate hundreds or thousands of times per second. Now here's the trick. The faster something vibrates, the more precisely you can measure time. Why? Because you're counting more ticks per second. If your clock ticks once per second and you can measure individual ticks, your best precision is about a second. But if your clock ticks 1,000 times per second, you can measure time to 1,000th of a second. In the early 20th century, engineers discovered something remarkable about quartz crystals. Quartz is piezoelectric. That means if you squeeze it, it generates a tiny electric voltage. And if you apply an electric voltage to it, it changes shape slightly. Let me tell you how strange piezoelectricity is. You take a crystal, a regular arrangement of silicon and oxygen atoms locked in a precise geometric pattern. You squeeze it, and somehow, out of this purely mechanical action, electricity appears on the surface. It's like magic, but it's not magic. It's physics. The effect was discovered in 1880 by Pierre and Jacques Curie. Yes, Pierre Curie, the husband of Marie Curie, the one who studied radioactivity. Before he got involved in radioactivity, he was working on crystals. The Curies realized that certain crystal structures lack a center of symmetry. When you deform them, you push the positive and negative charges within the crystal in slightly different ways, and a net voltage appears on the surface. The inverse works too. Apply a voltage, and the crystal deforms. Remove the voltage, and it springs back. Apply an oscillating voltage, and the crystal vibrates. And here's the crucial point. The crystal likes to vibrate at certain specific frequencies, its resonant frequencies, determined by its size and shape and the elastic properties of the material. Think of it like a bell. Tap a bell, and it rings at a particular pitch. That pitch is the bell's resonant frequency. The bell doesn't want to vibrate at other frequencies. It wants to ring at its natural frequency. Quartz crystals are incredibly stiff, incredibly hard, and incredibly stable. Their resonant frequencies don't drift much with temperature. They don't wear out. A quartz crystal will ring at nearly the same frequency for years and years. So imagine you take a little slice of quartz crystal, attach electrodes to it, and hook it up to an electronic circuit. The circuit applies a voltage. The crystal flexes. Then the crystal tries to spring back, which generates a voltage. That voltage feeds back into the circuit, which amplifies it and reapplies it to the crystal. And the whole thing starts vibrating at a very precise frequency. A quartz crystal is like a tiny, perfect tuning fork, and it can vibrate at exactly 32,768 times per second. Why that particular number? Because it's a power of 2. It's 2 to the 15th power. And that matters because electronic circuits can easily divide a frequency by 2 over and over. You divide 32,768 by 215 times, and you get exactly 1 pulse per second. Clean, simple, beautiful. The first quartz clock was built in 1927, and it quickly became the most accurate timekeeper in the world. Pendulum clocks, which had reigned supreme for 270 years, were suddenly obsolete for precision timekeeping. But let me tell you, quartz has its own problems. The frequency of a quartz crystal depends on its temperature. As the crystal heats up or cools down, its dimensions change slightly and its frequency shifts. The best quartz clocks carefully control the temperature of the crystal, keeping it in a little oven steady to a tiny fraction of a degree. Still, even with perfect temperature control, there are limits. The crystal is a physical object made of atoms, and atoms jiggle, thermal fluctuations, quantum effects, tiny defects in the crystal structure. All of these create noise. A quartz clock might drift by a few seconds over a year. For telling time in your kitchen, that's fantastic. For the most demanding scientific applications, it's not good enough. So scientists asked, what's the most stable oscillator we could possibly find? And the answer turned out to be atoms themselves. Now, let me explain why this is so brilliant. Pendulums are good, but they depend on local gravity, which varies. Quartz crystals are better, but they depend on the exact shape and size of the crystal, which can drift with time. What we need is something that doesn't depend on any external conditions, something that's absolutely universally constant. Enter quantum mechanics. In quantum mechanics, atoms can only exist in certain discrete energy states. Not any energy, only specific allowed values. This is fundamentally different from classical physics, where a swinging pendulum can have any energy you like, depending on how hard you push it. An atom is like a staircase with fixed steps. It can be on step 1, or step 2, or step 3. It cannot be on step 1.5. The steps are determined by the fundamental laws of physics, by Planck's constant and the charge of the electron and the structure of the atom. And here's the key point. When an atom transitions between two energy levels, it emits or absorbs a photon with a very specific frequency. The frequency is related to the energy difference by Planck's formula. E equals h times F. Energy equals Planck's constant times frequency. That frequency is fixed by the laws of physics. It doesn't depend on temperature. It doesn't depend on pressure. It doesn't depend on whether you're in a laboratory in London or on a spaceship heading to Mars. It's a universal constant built into the fabric of reality. See, atoms have a beautiful property. Every atom of a given element is exactly identical to every other atom of that same element. A cesium atom here on Earth is absolutely, precisely the same as a cesium atom on the other side of the galaxy. The laws of physics guarantee this. Quantum mechanics demands it. And atoms vibrate, well, not exactly vibrate, but they have internal oscillations. The electrons in an atom can be in different energy states, and when an atom transitions between two particular energy states, it emits or absorbs electromagnetic radiation at a very specific frequency. For cesium 133 atoms, there's a particular transition between two energy levels in the ground state, and the frequency of that transition is exactly 9 billion, 192,631,770 cycles per second. Not approximately. Exactly. That number was chosen in 1967 to define the second. 1 second is the time it takes for a cesium atom to oscillate 9,192,631,770 times during that particular transition. Why cesium? Why not some other atom? Well, cesium happens to have some nice properties. It has only one electron in its outer shell, which makes its behavior relatively simple. The particular transition used between two hyperfine levels in the ground state produces microwave radiation at a frequency that's easy to work with. The radiation is around 3 centimeters in wavelength, which is convenient for engineering. But really, the choice of cesium was somewhat arbitrary. We could have defined the second using rubidium atoms, or hydrogen atoms, or any number of other elements. The point is that once you pick an atom and a specific transition, you've defined a universal standard. Every cesium atom in the universe has exactly the same energy levels. They're all the same. This is one of the most profound facts in physics. Atoms of the same element are identical. Not approximately the same, not similar, but absolutely identical. A cesium atom on Earth is exactly the same as a cesium atom in the Andromeda galaxy. This identity is required by quantum mechanics. It's not a matter of careful manufacturing. It's a law of nature. So when we say 1 second equals 9 billion, 192,631,770 oscillations of cesium, we're defining time in terms of a universal constant of nature. It's the same everywhere. It's the same for everyone. It doesn't depend on human conventions or measuring apparatus. The cesium atom is its own standard. Think about what that means. We used to define the second in terms of the rotation of the Earth. 1 second was a fraction of a day. But the Earth's rotation isn't perfectly constant. The tides slowly drag on it, making the days gradually longer. Earthquakes can shift mass around and change the rotation speed. The Earth is a lousy clock, really. So in 1967, we changed the definition. The second is now defined by atoms, not by Earth, not by the sun, not by any astronomical phenomenon, by the quantum mechanical properties of cesium atoms, which are the same everywhere in the universe. An atomic clock works something like this. You take cesium atoms and heat them up so they form a gas, a beam of atoms flying through a vacuum chamber. You expose them to microwave radiation. If the microwave frequency exactly matches the cesium transition frequency, the atoms will absorb the radiation and change their energy state. You can detect how many atoms made the transition. Then you adjust your microwave source, tuning it up and down, looking for the frequency that causes maximum absorption. When you find it, you've locked on to the cesium resonance. And then you count the cycles of that microwave radiation. Every 9 billion, 192 million, 631,770 cycles, 1 second has passed. The first atomic clock using cesium was built in 1955 at the National Physical Laboratory in England by Louis Essen. Today, the best atomic clocks are accurate to about 1 second in 300 million years. That means if you had started one of these clocks when the dinosaurs went extinct 66 million years ago, it would still be correct to within a fraction of a second today. But you know what's really wild? Even that's not good enough anymore. Scientists have built optical atomic clocks that use transitions in the visible light part of the spectrum, which has even higher frequencies than microwaves. Hundreds of trillions of cycles per second. These optical clocks are so precise that they can detect the time dilation caused by raising the clock just a few centimeters higher in Earth's gravitational field. And that brings me to the really deep part of this story. You see, when I asked you at the beginning how old you are, you probably thought time was simple. You thought there was one universal clock ticking away somewhere, and your age is just the number of ticks since you were born. But Einstein showed us something disturbing. Time is not universal. Time flows at different rates depending on how fast you're moving and how deep you are in a gravitational field. Let me explain the velocity effect first. Imagine you have a twin. Your twin gets in a rocket ship and blasts off at very high speed, let's say 90% of the speed of light. She travels to a distant star, turns around, and comes back. You stay home, sitting on Earth, watching TV, eating sandwiches. When your twin returns, you compare ages. And here's the stunning result. Your twin is younger than you. She's aged less. Her clocks, her heartbeat, the vibration of atoms in her body, all of it ran slower while she was moving at high speed relative to you. This is not science fiction. This is hard physics, verified countless times. Now wait, you might say. Motion is relative. From your twin's point of view, she was sitting still in her rocket, and it was Earth that flew away and then came back. So why doesn't she think you should be younger? This is the famous twin paradox, and it confused people for decades. But there's no paradox if you think carefully. The situation is not symmetric. Your twin had to accelerate. She had to fire her rockets to turn around at the distant star. During that acceleration, she could feel a force pushing her back into her seat. She knew she was accelerating. You, sitting on Earth, felt no such force. The twin who accelerates, who changes their state of motion, is the one who ends up younger. The laws of physics can tell the difference between the one who stayed in a constant state of motion and the one who didn't. And here's another way to think about it. When you draw the paths of the two twins through space-time, through that four-dimensional geometry I mentioned, the paths are different. Your path is nearly straight. Your twin's path bends, goes out to the star, bends again, comes back, and in space-time, a straight path accumulates more proper time than a bent path. This is the opposite of what happens in ordinary space, by the way. In ordinary space, a straight line is the shortest distance between 2 points. In space-time, with its peculiar geometry, a straight line is the longest time between 2 events. So when your twin flies away and comes back, taking a bent path through space-time, she accumulates less proper time than you do on your straight path. She ages less. There's no contradiction, just unfamiliar geometry. This is not science fiction. This is hard physics, verified countless times. In 1971, scientists named Hathaway and Keating took atomic clocks on commercial airliners and flew them around the world, eastward and westward. When they compared those clocks to identical clocks that stayed on the ground, the times were different. The clocks on the planes had ticked at different rates than the clocks on the ground, exactly as Einstein's theory predicted. The eastward flying clock lost about 59 nanoseconds compared to the ground clock. The westward flying clock gained about 273 nanoseconds. These differences are tiny billionths of a second, but they're real, and they perfectly match the predictions of relativity. But wait, why were the results different for eastward and westward flights? Because the Earth is rotating. A clock on the ground at the equator is already moving at about 1,000 miles per hour due to Earth's rotation. A plane flying eastward in the same direction as Earth's rotation is moving even faster relative to Earth's center. A plane flying westward is moving slower, and the faster you move, the slower your clock runs relative to a stationary reference frame. But there's another effect too. The planes were at high altitude, where Earth's gravitational field is weaker. And Einstein's general relativity tells us that clocks in weaker gravitational fields run faster. So the altitude effect makes the airborne clocks gain time, while the velocity effect makes them lose time. The total result depends on which effect dominates. Now think about this carefully. Your age depends on your path through space and time. If you lived your entire life on a mountaintop, you'd age slightly faster than if you lived at sea level. If you traveled a lot at high speeds, you'd age slightly slower than if you stayed still. Your age is not just a number. It's the integral of your proper time along your world line through space-time. Too technical? Let me say it more simply. Your age measures how many oscillations of a cesium atom have occurred along your personal path through the universe, not the oscillations of some universal master clock. The oscillations of atoms traveling with you through the gravitational fields you've experienced at the velocities you've traveled. If you and I started at the same moment and you took a different route through the universe than I did, we would end up with different ages, not because our clocks are wrong, but because time itself flowed at different rates for each of us. This is one of the most profound truths in physics. There is no universal now. There is no cosmic clock that everyone agrees on. Each observer carries their own time with them. Let me give you a thought experiment to make this vivid. Suppose you could travel to a black hole, one of those regions of space where gravity is so intense that not even light can escape. You don't fall in. You just orbit around it, fairly close, for what seems to you like a year. Then you fly back to Earth. How much time has passed on Earth while you experienced 1 year? It could be decades. It could be centuries. It depends on how close you got to the black hole and how strong its gravitational field was. Time near a black hole runs extremely slowly compared to time far away. Richard, now wait. That sounds crazy. How can time run slower just because gravity is stronger? Here's one way to think about it. Light is affected by gravity. A photon climbing up out of a gravitational field loses energy. It gets redshifted. Now, imagine an atomic transition that emits a photon. That photon has a specific frequency related to its energy. If the photon is emitted deep in a gravitational field and observed higher up, its frequency appears lower. But frequency is the rate of oscillation. Lower frequency means fewer cycles per second. So from the point of view of an observer high up, the atomic clock down below is oscillating slower. Time is running slower down there. Let me make this more vivid with a thought experiment. Imagine you're standing at the top of a tall tower. Your friend is at the bottom. Each of you has an identical atomic clock, and each of you is watching the other's clock through a telescope. Your friend sends you pulses of light, 1 pulse every second according to their clock. You receive these pulses, and here's what you observe. The pulses arrive more than 1 second apart according to your clock, maybe 1.00000001 seconds apart, a tiny bit more. You might think, well, the light had to climb up through the gravitational field, so it took extra time to reach me. But that's not quite right. The extra time per pulse is the same on the way up. Each pulse takes the same amount of extra time to climb. No, what's happening is that your friend's clock is genuinely ticking slower. They're sending pulses 1 second apart by their clock, but their seconds are longer than your seconds. From your point of view, your friend is living in slow motion. And from their point of view, you are living in fast forward. This is real. This is happening. The difference is usually very small near Earth's surface, but it's measured. This isn't an illusion. It's not some weird distortion of perception. If you synchronize two clocks, put one at the bottom of a tower and one at the top, leave them for a while, then bring them back together, the bottom clock will have recorded less elapsed time. It will be behind. You can do this experiment. Scientists have done this experiment. In fact, the global positioning system depends on this. GPS satellites orbit at high altitude, about 20,000 kilometers up. At that altitude, the gravitational effect makes their clocks run faster than clocks on Earth's surface, by about 45 microseconds per day. The velocity effect makes them run slower, by about 7 microseconds per day. The net result is that the satellite clocks gain about 38 microseconds per day compared to ground clocks. That doesn't sound like much. But GPS works by measuring the precise timing of signals from multiple satellites. If those signals are off by 38 microseconds, and signals travel at the speed of light, the position errors would accumulate to about 10 kilometers per day. Your phone's GPS would be useless, so the engineers had to build relativity into the GPS system. They actually slow down the satellite clocks before launch, setting them to tick at a lower frequency than they would on the ground. Once in orbit, the relativistic effects speed them up, and they end up ticking at exactly the right rate to match ground clocks. Every time you use GPS, you're relying on Einstein's relativity. You're relying on the fact that time is not absolute, that clocks run at different rates depending on gravity and motion. I find this wonderful. Einstein developed general relativity in 1915, working out the mathematics of curved space-time with pencil and paper. He had no idea that a century later, billions of people would carry devices in their pockets that depend on his theory for their basic functioning. He was trying to understand the nature of gravity. He ended up enabling navigation systems that guide cars, planes, and ships. This happens all the time in physics. You study something because you want to understand it, because the question is interesting, because nature is beautiful and you want to know how it works, and then decades or centuries later, your discoveries turn out to be essential for technologies you never imagined. Faraday studied the relationship between electricity and magnetism because he was curious. Now we have electric motors and generators everywhere. Maxwell unified electricity and magnetism into electromagnetic waves because the equations demanded it. Now we have radio, television, cell phones. The scientists weren't trying to invent practical devices. They were trying to understand the universe. The practical applications came later, and so it is with relativity. Einstein wanted to understand what happens when you travel at the speed of light. He wanted to reconcile Maxwell's equations with Galilean relativity. He ended up revolutionizing our concept of space and time, and now his equations are running continuously in satellites overhead, making sure your phone can find the nearest coffee shop. Let me pause and address a common misconception. Some people think that time dilation is just about clocks. They think, well, maybe the atoms in a clock behave differently under high gravity or high speed, but real time keeps ticking along normally. No, that's wrong. Everything dilates. Chemical reactions slow down. Biological processes slow down. Radioactive decay slows down. If your heartbeats serve as a clock, your heartbeats slow down. If your thoughts serve as a clock, your thoughts slow down. There is no real time independent of these physical processes. Time is what clocks measure, and clocks are physical systems that undergo periodic processes. The rate of those processes is affected by motion and gravity. Period. End of story. There is no hidden, true time running in the background. This was Einstein's great insight. He took time seriously as a physical quantity, not just a mathematical abstraction. Time is measured by physical processes. Physical processes are governed by the laws of physics, and the laws of physics include relativity. Now, you might ask, if time runs at different rates in different places, which rate is correct? Which clock shows the real time? And the answer is, they're all correct. Each clock correctly shows its own proper time, the time measured along its own path through space-time. There's no master clock that's more correct than any other. This is deeply unsettling to our intuitions. We're used to thinking of time as a river that flows at a constant rate, carrying all of us along together. But that's an illusion, a consequence of the fact that we all move slowly compared to light and we all live at similar gravitational potentials. In our everyday experience, the differences in time are too small to notice, but they're there. Let me now bring this back to the question of your age. When you say you are 30 years old, what you're really saying is this: starting from the event of your birth, following your path through space-time, accumulating your proper time, about 9.5 times 10 to the 17th cesium oscillations have occurred. That's roughly 30 years times 31.5 million seconds per year times 9.2 billion oscillations per second. That number, that count of oscillations, is your age, not some abstract 30 years. A concrete physical count of atomic vibrations along your personal world line. And here's the kicker. If your identical twin had taken a different path, traveling at high speeds, or spending time near massive objects, their count would be different. They would be a different age. Not because anyone's clock is wrong, but because they accumulated different amounts of proper time. The twin paradox, as it's called, is not really a paradox at all. It's a straightforward prediction of relativity, and it's been confirmed experimentally with muons, with atomic clocks, with everything we can test. Now, I want to step back and talk about what all of this tells us about the nature of time. For most of human history, time was something external, something that happened to us. The sun rose and set. The seasons changed. We aged and died. Time marched on, indifferent to our wishes. And then we learned to measure it. We built sundials, then pendulum clocks, then quartz clocks, then atomic clocks. Each step brought us closer to the fundamental nature of time. What we discovered is that time is not separate from the physical world. Time is part of the physical world. The flow of time is the evolution of physical systems. And that evolution can proceed at different rates, depending on circumstances. Einstein unified space and time into a single entity, space-time. Motion through space affects your motion through time, and vice versa. Gravity warps space-time, curving it, changing the rates at which clocks tick. The universe is a four-dimensional structure, and our experience of now is just a local slice through that structure. Does this mean time is an illusion? No, I don't think so. Time is as real as space, but our intuitive picture of time as a universal, uniformly flowing river, that's the illusion. The reality is richer, stranger, and more beautiful. What is time, really? I get asked this question a lot, and my honest answer is I don't think anyone fully knows. We know how to measure time. We know how time behaves under different conditions. We can write down equations that describe how time is affected by velocity and gravity. But why does time exist at all? Why does the universe have this dimension in which things change? That's a deeper question, and it's not fully answered. Some physicists think time is fundamental, a basic ingredient of reality that can't be reduced to anything simpler. Others think time might emerge from some more fundamental structure, just as temperature emerges from the motion of atoms. In this view, time would be a kind of statistical phenomenon, an appearance that arises when you have many particles interacting in complex ways. The physicist Julian Barber has argued that time might not exist at all in the deepest description of reality. What exists, he says, is a collection of nows, of instantaneous configurations of the universe, and what we call time is just the pattern of relationships among these configurations. I don't know if he's right, but it's a fascinating idea. What I do know is that the operational definition of time, time as measured by clocks, is solid and reliable. We know what we mean by 1 second. We know how to count seconds with incredible precision. And we know that different clocks can measure different amounts of time between the same two events, depending on their paths through space-time. Here's another thought that might keep you up at night. The universe is about 13.8 billion years old, as measured from the Big Bang to now. But measured by whom? Measured by a clock on Earth, or a clock in intergalactic space, or a clock near a black hole? These clocks would all disagree. The age of the universe is a number, but it's a number that depends on the path through space-time. In fact, when cosmology, they're talking about the proper time measured by a hypothetical clock that's been co-moving with the expansion of the universe since the beginning. sitting still with respect to the average matter distribution. Other clocks would give different answers. Let me tell you one more thing that atomic clocks have taught us. Remember I said the rotation of the Earth isn't perfectly constant? Well, atomic clocks are now so precise that they can detect tiny irregularities in Earth's rotation. And you know what they found? Some days are a few milliseconds longer than others. The atmosphere drags on the mountains. Ocean currents shift mass around. The liquid core of the Earth sloshes. All of this affects the rotation rate. Over long periods, the days are gradually getting longer. The tidal friction from the moon slowly breaks Earth's rotation. 1 billion years ago, the day was only about 18 hours long. 1 billion years from now, it might be 30 hours long. We used to define time in terms of Earth's rotation. Now Earth's rotation is measured in terms of atomic time. The student has become the master. And here's a lovely irony. The concept of leap seconds exists because we want our civil time, the time on our clocks and calendars, to stay synchronized with Earth's rotation. But Earth's rotation is irregular, so occasionally we have to add a leap second to keep atomic time aligned with astronomical time. Think about that. Our clocks are so good, so much better than the Earth itself, that we have to deliberately make them wrong, make them skip a beat, just to keep them in sync with our spinning planet. The cesium atom doesn't care about Earth. It oscillates at exactly the same frequency whether Earth speeds up or slows down. The atom is the master clock. Earth is just another system whose rotation we measure against the unchanging standard of atomic vibrations. Now, what does this all mean for you? Why should you care? I think there are 2 reasons. First, practical. Every piece of technology that requires precise timing, and that's almost everything in the modern world, depends on our understanding of what time really is. GPS, telecommunications, power grids, financial transactions, computer networks, all of this relies on atomic clocks and the physics of timekeeping. The next time your phone figures out exactly where you are, remember that it's using Einstein's relativity to do it. Second, philosophical. Your experience of time, the flow of moments, the sense of now, that experience is rooted in physics. The atoms in your body are oscillating. The chemical reactions in your brain are proceeding. Your thoughts, your memories, your sense of self, all of it is built on physical processes that take time. And that time is not absolute. It depends on where you are and how you're moving. You are, in a very real sense, a clock. A fantastically complex clock made of trillions of cells, each one running countless chemical reactions, all of them synchronized by the fundamental laws of physics. And your age? Your age is the number of ticks you've accumulated along your path through the universe. Not calendar ticks, not Earth rotation ticks, proper time ticks, the kind of ticks that Einstein taught us about. So the next time someone asks how old you are, you might smile a little, because you know that the question is deeper than it sounds. You know that your age depends on where you've been and how fast you were going. You know that time itself is flexible, stretchable. Warpable. And you know that the simple act of counting seconds is one of the most profound achievements of human civilization. We started by watching shadows and counting heartbeats. We ended by listening to atoms sing. And that, I think, is pretty wonderful. One final thought. If you could design the perfect clock, what would it be? You'd want something that oscillates at an extremely high frequency, so you can measure very short intervals. You'd want something that's immune to temperature, to gravity variations, to electromagnetic interference. You'd want something that's the same everywhere in the universe, a built-in constant of nature. The cesium atom is pretty good. But even better, clocks are coming. Optical lattice clocks using strontium atoms, clocks using single-trapped ions of aluminum, clocks that will be accurate to 1 second in 30 billion years, more than twice the current age of the universe. What will we do with such clocks? I don't know. But I guarantee that every time we've built a better clock, we've learned something new about the universe. Better clocks reveal the irregularities in Earth's rotation. Better clocks made GPS possible. Better clocks confirmed Einstein's predictions of time dilation. I suspect that the next generation of clocks will show us things we can't even imagine yet. Because when you can measure time to unprecedented precision, you're really measuring the fabric of reality itself. One possibility is detecting gravitational waves. These are ripples in space-time itself, caused by massive objects accelerating. They were predicted by Einstein in 1916 and finally detected directly in 2015. But gravitational waves are incredibly faint by the time they reach Earth. Detecting them required measuring a change in distance of less than 1/10,000th the diameter of a proton. With more precise clocks, we might be able to detect gravitational waves in new ways, opening a new window on the universe. We might see gravitational waves from the early universe, from the Big Bang itself. Another possibility is testing whether fundamental constants really are constant. The fine structure constant, which describes the strength of the electromagnetic force, has a certain value today, but has it always had that value? Has it been the same throughout the history of the universe? With precise enough clocks, we could compare the frequencies of different atomic transitions and see if their ratios are changing over time. Any change would revolutionize physics. And here's a really wild idea. Some theories of quantum gravity suggest that space-time itself might have a discrete, grainy structure at the smallest scales, rather than being smooth and continuous. This is called quantum foam, or space-time foam. The graininess would be at the Planck scale, far too small to observe directly. But some versions of these theories predict tiny effects that might be detectable with extraordinarily precise clocks. I'm not saying any of this will happen. These are speculative ideas. But the history of physics shows that better instruments lead to new discoveries, and clocks are among the most precise instruments we have. And that brings me back to where we started. Your age is a count of oscillations, a count of the quantum mechanical vibrations of atoms along your personal path through the four-dimensional geometry of space-time. It's not just a number, it's a physical fact about the universe. And I find that absolutely fascinating. Now, I want to hear from you. If you could send one clock on a journey through space, near a black hole, around a neutron star, across the galaxy and back, what do you think would be the most surprising thing about how much time had passed when it returned? Leave your thoughts in the comments below.